Hey, what's up guys, welcome back to this video. In this video we're going to solve this coding interview question jump game. Given an integer array nums, you are initially positioned at the array's first index and each element in the array represent your maximum jump length at the position. So you're given an array of integers and you're initially positioned at the first index and each element in the array represent maximum jump length. You have to return true if you can reach the last index or false otherwise. So if we can reach the last index, we'll return true. If we cannot reach the last index, we will return false. Now let's see some examples. For examples, if you're given this array of integers, we are initially positioned at the first index right here. And here we have 2. It means that from here we can jump and the maximum jump length is 2. So from here we can jump to this cell or from here we can jump to this cell. If we jump from this cell to this cell, from this cell we can jump to this cell, or we can jump from this cell to this cell, and also can jump from this cell to this cell. Now here we see that if we jump from this index 0 to the index 1 and from this index 1 to the index 4, we reach the last index. So we will return true because we can reach the last index. No matter which path we're choosing to visit the last index, since we visited the last index, we'll return true. So for this given integer array, we'll return true. Let's take another example. For example, if we're given this array of integers, from this first cell, we can go to this cell, or we can go to this cell, or we can go to this cell, because the maximum jump length here is 3. From this cell 3, if we move to this cell 2, then from here we can visit this cell, or from here we can visit this cell 0. Then if we visit from this 3 to 1, then from 1 we can visit this. Okay, we see that we're stuck at this cell. Here we have maximum jump length 0. We cannot jump from this cell. Here we see that we're stuck at this cell, so we cannot reach the last index for this given integer array. So for this given array, we'll return false. Now, how we can solve this problem? First, let's talk about the naive solution to this problem. For sake of understanding, let's assume we're given this array of integers. We are initially positioned at this cell of index 0. Now, what we're going to do, we're going to scan this array from left to right. We'll iterate this array from the second cell, that means from index 1 all the way to the end, from index 1 to 4. So we'll scan this array from index 1 to index 4. Here we have the element 3. Now here what we will do, we will check, can we visit this cell from the left? We see that we can visit this cell from the left. How we can do that? In order to do that, we will use a nested for loop. The outer for loop will iterate from index 1 to the index 4, okay, for this given array. The outer loop will iterate from index 1 to the index 4 for this given array, and the inner loop will iterate from index I-1 to 0. So from index I-1, from I-1 to 0. So our outer loop will iterate from index 1 to 4, and inner loop will iterate from index I-1 to 0. Now here what we'll do, we'll see the difference of index. So 1 minus 0 is 1. And the value here we see that 2. 2 is greater than the difference of the index. So we can erase this index. Then our next element is 1. Can we erase this cell from the left? Now let's run this inner loop here. I minus 1 to 0. So here I minus 1 is 1. 2 minus 1 is 1. And the value here is 3. This value is greater than this value, 1. So we can visit this cell from the left. Now let's move forward. Now this is our current cell. Can we visit this cell from the left? This is our immediate left cell. The difference of index is 1 and the value is 1. So we can erase this cell. So let's move forward. This is our current element. Can we visit this cell from left? We see that the difference of these two index is 1 and here we have 1. So 1 is equals to 1. So we can visit this cell from this cell. So we see that here we see that we erase the last index. So we'll return true. This solution will take big of n square time complexity for the worst case, and it will take big of 1 space complexity. For better understanding, let's take another example. For sake of understanding, let's assume we're given this array of integers. Initially, we're positioned at this index 0. We're going to iterate this array from index 1 to the index 4. This is our current element. Now, can we erase this element from the left? We see that we can erase this element from the left. And we can check that by calculating the difference of index. So 1 minus 0 is 1. And here we have value is 3. We see 3 is greater than 1. So we can erase this cell from the left. Now this is our current element. Can we erase this cell from the left? The difference of index for this two cell is 1. And here we have value 2. So we can erase this index. Now this is our current. Here the difference of index is 1 and here we have value 1. So we can erase this index 3. Now this is our current element. Can we erase this cell from the left? We see that the difference of these two index is 1 and the value here is 0. So we cannot erase this cell from this cell. Let's move to this cell here. Now let's find the difference of index. 4 minus 2 is 2. We see 2 is greater than 1. So we cannot erase this cell from this cell. So let's move to the left. Here the difference of index is 4 minus 1 is 3. Here we have the value 2. So we cannot erase this cell from this cell 2. Let's move to the left. Here the difference of index 4 minus 0 is 4. And here we have value 3. 3 is less than 4. So we cannot erase this cell 4 from this cell 3. And we see that there is no element on the left of 3. Finally, we see that we cannot erase this cell from the left. So for this given integer array, we'll return false. The time complexity of this solution is big of n square. And the space complexity is constant, bigger of 1. Now let's see the algorithm for this naive solution. This is the algorithm for naive solution. This function canJump takes nums array as input. Here we're calculating the length. Len equals to nums.length. Then we're running a loop from index 1 to the end of the array. Here we have a variable canRes equals to false. Then we're running a loop from I minus 1 to 0. If we see the difference of index I minus j less than equals to nums j, then we'll set canRes equals to true. If we found canRes equals to false, then we'll directly return false. Otherwise, we'll return true at the end. Now let's see how this actually works. We'll iterate from this index to this index 4. I is pointing here. This is your current element. The difference of index is 1. And we see that 1 is less than equals to 2. So we can reach this cell. So let's move forward. Here we see the difference of index is 1, and here the value we have 3. So 1 is less than equals to 3. So we can reach this cell from this cell. Now let's move forward. This is your current element. Difference of index is 1, and here we have 1. So 1 less than equals to 1. So we can reach this cell. Let's move forward. This is our current element. We see that we can reach this element from the left, because 4 minus 3 is 1. 1 is less than equals to 1. So it's true. So we can reach this cell from this cell. We see that we came to the end of this array. Now we're done. Since we find out the last cell here, so we'll return here true. If we cannot reach the last cell, then we'll return false by this return statement. And the solution will take big of n squared time complexity and big of 1 space complexity. But this is a brute force solution. Can you improve this solution? Now let's see how to optimize this solution from quadratic time complexity to linear time complexity. Now we're going to talk about the efficient solution for this problem. For sake of understanding, let's assume we're given this integer array. Now what we're going to do, we're going to scan this array from left to right. We'll solve this problem in one patch. That means we'll scan this array only once. We'll use a variable called reachable. Initially reachable equals to 0. Here I'm going to insert 0, and reachable equals to 0 initially, and here we're positioned at this index 0 initially. Now we're going to calculate reachable. Let's assume R for reachable. We're going to calculate the reachable by using this formula. Reachable equals to our current element if this is our array, and if AI is our current element, we'll add here the index I. We'll take the maximum of AI plus I and comma the reachable here. Okay, here we see that AI is 2 and I is 0. So 2 plus 0 is 2 and R is 0. That means reachable. So our reachable value changed. Here we'll insert 2. Now you might be thinking why we're adding 2 plus 0, the current value plus the current index. First, let's talk about what is reachable. Here reachable 2 means from here we can reach to this cell, okay, to index 2. We'll calculate reachable in each step. If we find out reachable equals to the last index, or if we find out reachable is greater than the last index, then we'll return true. Why we'll return true if we saw reachable is equals to last index or reachable is greater than our last index? Because we'll move to the last index if we find out reachable equals to the last index or reachable is greater than last index. This is our current element. Now here let's calculate reachable. From this cell, find out the reachables. So from this cell, how we can move on which index? Here 3 plus 1 is 4. Reachable is 2. So max of 2 and 4 is 4. So let's insert here 4. This is the value for reachable at this point. And we see that from here we can reach to the last index. We don't have to move further in this integer array because we find out the last index here. Here we find out the last index. So we can reach the last index. Here we will return true because we find out the last index here. And here we're adding this current value to this current index, because if we add this current value to this current index, we'll find out the index we can visit from this current index. Okay, we added here 1 to this value 3, we get 4. So we can jump to the index 4, and we see that the index 4 is the last index. So we'll return true. And this is the intuition here. Okay, this solution will take big of n time complexity. For the worst case, we have to scan this array from left to right once. and it will take big O of 1 space complexity. So time complexity is big O of n and space complexity is big O of 1. Now let's take another example for better understanding. Let's say we're given this array of integers. We're initially positioned at this index 0 and reachable equals to 0 initially. And here let's calculate reachable. So 3 plus 0 is 3. So max of 0 and 3 is 3. So the reachable here is 3. In each step we will check, is reachable equals to the last index, and is reachable is greater than the last index. If we find these two cases, we will return true. Here we see that 3 is not the last index. Now let's move forward here. We see we have 2 plus 1 is 3, and here we have 3. So max of 3 and 3 is 3. So reachable equals to 3 here. 3 is not equals to the last index, or 3 is not greater than last index. So let's move forward. Here we find it again 3. So max of 3 and 3 is 3. So here, from here we cannot reach the last index. Reachable equals to 3. Let's move forward. Here we have 0 plus 3 is 3. Max of 3 and 3 is 3. We cannot reach the last index here, okay? Here we see that we cannot reach the last index here. Here we see that the reachable is 3. So we cannot go beyond 3 because reachable is 3 here. We cannot go out of index 3. And here, if you want to move to this element, we can't. Why is that? Because here at this point, reachable is a 3. We can reach at most the index 3, and we are stuck here. We cannot go forward. So we find out that this value reachable is not greater than or equals to last index. So we cannot reach the last index for this given integer array. So we'll return false. This is the solution to this problem. And the solution will take big O of n time complexity and big O of 1 space complexity. Now let's see the algorithm. This is the algorithm to solve this problem. This function takes an integer array, nums. Here we're declaring reachable equals to 0. Then we're computing the length. Then we're running a loop from index 0 to all the way to the end. Here we have this condition, I less than equals to reachable. Here we're computing reachable in each step, max of reachable and I plus current element. Then we're checking here if reachable is greater than or equals to length minus 1. Then we're returning true. It means that we can reach the last index. That's why we're returning true. If we do not find out this condition, reachable is greater than or equals to length minus 1, we'll return false. Now let's see an example here. Okay, 2, 3, 1, 1, 4. Reachable initially 0. Here reachable equals to 2. 2 plus 0 is 2. So we can reach this index. Here reachable equals to 4. So we can reach the last index. We don't have to worry about the element on the right, because from here we can reach the last index. So we'll return true. Here length minus 1 is the last index. Length is 5. 5 minus 1 is 4. So this is 4. And here we see reachable equals to 4. So this condition is true, we'll return true. And this is the solution to this problem. This is the efficient solution for this problem. The solution takes big O of n time complexity and big O of 1 space complexity. Hope you have understood how to solve this problem efficiently. If you have any question, if you have any suggestion, let us know. Thanks for watching this video. I'll see you in the next video.